Hi there, welcome to the first lecture in machine learning. Our goals for this lecture are relatively modest to sort of set up and formalize the machine learning problem. Okay, so we'll go through some introductory stuff. We'll introduce a concrete example in credit risk prediction as a running example throughout the theory. And we'll summarize the learning problem, and that will constitute what we will talk about today. Before we begin, formally speaking, let's go through a little bit of the administrative stuff and what are the resources that are available to you to succeed in this course. So the main resource is the course webpage, okay, and on this webpage you will find everything that you need to succeed in this course, okay, including the course information, slides, assignments, due dates, link to submitting where you can hand in the assignments, and so on and so forth. The textbook for the class is Learning from Data. Okay, so this is what it looks like if you've gotten yourself a copy of the book. I highly recommend it. We're going to be covering the first 5 chapters in the book, and then we'll move from the book to the e-chapters, which are freely available online at the book forum. Okay, so the book forum serves 2 purposes. The first is that it allows, that's where you can find the free e-chapters dealing with more advanced topics and techniques that we will introduce later on in the course. And it also is a discussion forum where you can participate and look at what others are saying about exercises and problems. You can ask questions, people answer. So hopefully you can make use of both of these, especially in this online edition of the course. Other resources, there are the TAs, there's myself. Please, I welcome questions. Email me questions. I love it when you guys ask questions, so don't hesitate on that. And if it's taking a long time for me to answer your question, it's not because I don't want to answer your question. I just get a long string of emails, and there are many students in this class, and I can only get to emails one by one. So email us, let us know if you have any concerns, questions, confusions. Okay, the prerequisites for this course are important. There are mathematical prerequisites, linear algebra, probability, and calculus. So you need familiarity with those topics. We're not going to cover those topics. Now, assignment 0 is a self-test. You can try to work those problems, not work, but read through those problems and see if you understand and determine whether or not you could solve those problems. Okay, so do assignment 0. It'll help you judge whether or not this course is for you. This is a theory course. Yes, it's a theory course in machine learning, but machine learning is in and of itself a practical subject. We use it in the real world. So even though it's a theory course, we will build the links and mention the links wherever it's clear between the theory that we develop and the practical applications. So linear algebra, probability, and calculus are in some sense essential to get the most out of this course. And you need to be able to program, because we will ask you to implement algorithms and test certain things that we discuss in class and when we talk about the theory. And it's very important to see theory in practice, so you need to be able to program comfortably. We are not going to offer debugging help. We will offer help from the algorithmic perspective. I don't quite understand this machine learning algorithm, but questions like, I programmed this machine learning algorithm and I don't know what's going on. My code doesn't compile and it doesn't run well. We are not going to be the primary resource for debugging of that kind. Okay. Now, that having been said, let me tell you about the storyline. And it's a very nice, clear storyline. So machine learning is this subject that is now pervasive, but an important question to begin with is, what is it? What is learning? Okay. And we're going to try to pin that down. And once we pin that down, we're going to be faced with a fairly shocking consequence that maybe it's not possible, so can we do it? So in what sense can we actually do machine learning? In what sense can we actually learn from data? Okay? And in that setting of, the setting of when we can learn from data, how do we do it? Okay, so what is learning? Can we do it? How do we do it? Once we have settled those basic issues, those absolutely fundamental issues, and whenever you decide that you're going to try to develop something, it's important to ask these fundamental questions, okay? And so we will see that, in a certain sense, yes, we can do it. Otherwise, this course would have been very short. Okay? And then the next question is, how do we do it well? How do we do it well? Okay? And that's going to take us along the lines of, certain buzzwords like overfitting, regularization, and so not only must you be able to do it, but you now need to address the practicalities of real data and the real problem, and within the realm, within the constraints set by theory, there are bad ways to do things and much better ways to do things. And that's what differentiates the expert from the amateur. Okay. And so we'll talk about how to do it well. Sections 1 through 4 largely comprise the theoretical component, the hardcore theoretical component of this course. Okay. And even though it's a theoretical component, during revealing this theoretical component, we will talk about a very concrete model, which is the linear model, and that allows you to place all this theory within the context of a concrete model and actually run experiments and run basic machine learning algorithms relating to the can we do it and how do we do it and how do we do it well. So once we've covered the theory, we're going to step back, and summarize this into a set of general principles. Now, this is very useful when you go into the practical domains, because you don't always want to be tangling with the math to solve very elementary problems. And so the general principles give you sort of rules of thumb, guidelines that are high level and link the theory to best practices. Okay. So sections 1 through 5 in this course, which is largely the first, let's say, 2/3 of the course, sets the theoretical foundation for learning. And then we will go and talk about more advanced techniques and other learning paradigms. Now, once you have grasped and fully understood sections 1 through 5, you're ready to go out there. You are competent. You're as good as an expert. Okay? The advanced techniques are icing on the cake. Maybe you can do a little bit more, a little bit with slightly less assumptions, maybe neural networks a little bit more non-linear, support vector machines, a little bit more robust, and so on and so forth. So advanced techniques add that extra dose of icing, but you should be able to survive and do well in machine learning just based on the fundamentals. Okay, and then we will maybe touch on other paradigms, but not that much. So the primary focus of this course is the supervised learning context, and we'll say more about what exactly supervised means in relation to other paradigms. Okay. We might touch on unsupervised learning, and we might touch on reinforcement learning, which is sort of the type of learning that we are most used to from human experience. And so, there's a healthy blend of theory and practice in this course, but nevertheless, I would still consider this course to be largely theoretical. Let me try to motivate you a little bit, okay? And I'm sure most of you do not need to be motivated that machine learning is everywhere today. And here's just a sampling of applications from, cancer detection, early cancer detection, heart condition prediction. Here's an ecology application where the task is, can we build an AI/machine learning to recognize leaves? If so, then we can count, see if we can recognize, then we can use a plane, take pictures, and then count leaves. And if we know the relative abundance of different types of leaves, i.e. different species of plants, then we know what's going on in the ecology. We know if the ecology is healthy or not, if there's too much pollution, and so on and so forth. Vision recognition, game playing. It turns out that some years ago, the best backgammon player in the world was an algorithm, a machine learned backgammon player that was trained using reinforcement learning. Okay, so that's interesting that, machines have conquered backgammon, machines have conquered chess, and machines are conquering a lot of things. Okay. Smart fridges, when will your fridge start, ordering milk for you, and figure out that, we think that you'd like this kind of milk since you like that kind of milk. Okay, here are a couple of applications that I have been subjected to. So here on the top right is a screenshot of Netflix when I logged in a few years ago. What they're doing is they're presenting for me recommended TV shows. So let's look at the first one, Wild Kratts. I have no idea what Wild Kratts is. Okay, so what's gone wrong here? Okay, so this is an interesting example where, if you think about it, it looks like Netflix has messed up its prediction engine and it's predicting nonsense shows for me. But then if you look a little bit more closely, you'll see that all these shows it's recommending are kids shows, and actually it's not doing a bad job for the audience that it is expecting, which is my kids. It didn't expect me to pop up, and so this is an example of a complicated machine learning problem, and they got it right for my kid, but now I came along and it's completely wrong. And I'm very disappointed, and I'm probably going to leave because I don't recognize any of these movies. So they made a mistake. They actually have since fixed this problem in a sort of manual way, because it is a very hard problem. But this is just to show you that, well, they did a good job for my kids in terms of recommending movies. They did a bad job for me. And is there a way for them to have improved this machine learning engine? Okay, here's another example, Google. I typed in at some point, relight my pilot light, which is the light that's used to light up my furnace that heats up the water in the basement. So sure enough, Google gave me search queries, but then it also recommended here Crisafulli Brothers Heating, okay, which is an extremely local, so not regional, not statewide, not countrywide. It's an extremely local plumbing and heating company. So somehow, Google has done some sort of figuring out that, maybe I'd be in the market for a heating and plumbing consultant. Now, they were not far off, because before I was searching for this relighting of the pilot light, I was also, browsing on some Home Depot and hardware store pages and so on and so forth. Okay, so Google in some sense might be considered to be the largest consumer of machine learning in the world, in terms of both, how much it uses and how many times it has to be deployed. Every time someone searches, Google deploys this recommendation engine, which recommends both the order in which the search queries should appear and what ads should be shown. You might think the order is the order. Why does it matter on a person? Well, they might have changed the order in which they responded to my search query, depending on whether I had last visited Home Depot or last visited Best Buy. So there's a lot of complexity to this problem. Okay. The interesting thing is that we're going to cover in this course the basic fundamental techniques of machine learning and the basic fundamental theory of machine learning that can essentially be adapted to solve all these problems. Now, these problems are not all of the same difficulty, but the underlying foundations and the underlying techniques are all very similar. Okay. So now it would be great if in this course I taught you the theory and the foundations and the techniques, and then we went and solved some big problem like cancer. But that's well outside the scope of a 13, 14-week course, so we need to set our sights a little lower. And the good thing is that the techniques and foundations that we reinforce in the problem that you're going to solve or attempt address in this course are the same techniques that can be used on these more difficult, more complex problems. Okay? And the problem that we're going to be using as the theme in this course is on the top left, which is this digit recognition task. And if you look at this, the top left digit is a 6, then a 5, 4, 7, 3, 6, 3, 1, 0. Very easy for me to do. The question is, can we build a machine learning algorithm that can solve that same problem? Believe it or not, that problem is more or less solved now by machine learning algorithms, and most mail sorters that look at zip codes and then send the envelope to the right spot are based on automated machine learning. Okay, so this is a problem that we know can be solved. We're going to develop foundational theory and techniques. Okay? And so those foundational theory and techniques should certainly apply to this problem, and you are going to demonstrate this in the course. And the beautiful thing here is that those same techniques can be used to solve this whole array of problems. And that's the beauty in some sense of becoming a machine learning expert. You become a machine learning expert, you can solve all these problems without really becoming an expert in any of those problems. You don't need to become a cancer expert to solve, to some extent, the early detection of cancer problem, providing that you have the right data. Okay, and we'll get into all these details. Okay, so our next goal is to pin down what exactly is machine learning, what exactly is learning. And to help us get there, I'm going to pose a question. So let's define a tree. So why don't you pause the video here? Pause the video and think about what is the definition of a tree. And now let me be more specific. By definition of a tree, I mean, you're going to write down a definition that, let's say, somebody could, program in a flowchart or an algorithm or a computer, okay, and then take that, flowchart, algorithm, computer, and go outside and identify everything that's a tree, and everything that fails to fit your definition will not be a tree. So think about what it takes to write down a definition of a tree, and just write it down. Pause the video. So pause the video now, write it down. Okay, so I'm back. If you pause the video, great. If you wrote down a tree, you're a great definer of, you wrote down a definition of a tree, you're a great definer of trees. And if you're here just for the ride, well, you know, probably most people who try to define a tree would say something like this. Okay, a tree is this object with a brown trunk. The trunk is moving upwards and then it branches, and then there are these green things called leaves, green little leaf-shaped things, let's say almost circular things that are hanging off the branches. Okay, and that's my definition of a tree. So let me show you some problems with this definition. So are these things trees? Okay. Now, the left guy is certainly a tree, and then when we look at the left guy and compare it to our definition, we realize that it's not that our definition was wrong, it's that it's not complete. So, you know, our definition works for a tree when you don't see the whole tree, but if you were to see the whole tree, then it's, you know, got roots. Okay? And so we would have to make a bigger definition, a more complicated definition. And then when we do that, we would still not know whether it's complete. Okay, what's going on the right? Well, the right is what came out when I did a Google search, a Google image search for tree. It's not a recent search, maybe some time ago, but you know, this is what Google popped up. And what is this? This is actually called a tree. So this is this thing that you put in your house when you have cats. Because, you know, the cat lives indoors, but the cat likes to sharpen its nails or scratch its nails or, you know, whatever on trees. And when there are no trees around inside the house, it's going to do it on your furniture. So in order to protect your furniture, you buy this thing, which is a tree. Then the cat, you know, instead of scratching your furniture, comes and scratches this thing. Well, that's nice, and you look at this in great admiration that you have managed to con the cat into thinking this is a tree. No way, Jose, no way. Okay. The cat is by no means conned into thinking that this thing is a tree. Okay. It knows this is not a tree, but you know, it says whatever, you know, you silly human, I'll pretend it's a tree for you. Now, how do I know that the cat, or why am I so sure that the cat has no inclination that this is a tree? Well, so we had a hard time defining trees. Now, let's see if we can recognize trees. Okay, so I showed this set of pictures to my 5-year-old daughter and said, which pictures have a tree? And without any hesitation, she pulled up this tree cartoon, okay, which is already amazing because it's not a real tree, it's a cartoon of a tree. And it's not upright, it's rotated, but nevertheless, she got it. Okay. This picture has a tree with giraffes, she does, you know. This picture has a tree and this picture has a tree. Now, what is this thing on the bottom right, this strange thing? Okay. Nevertheless, she got all the 4 trees correct. And all the 4 non-trees correct. Now, that's interesting for a 5-year-old to have absolutely no problem in identifying the trees. And I assure you, she has never seen these pictures before. So it's not that she had seen these pictures and committed to memory or memorized that, you know, these 4 things here are trees and these 4 things here are not trees. In fact, I'm pretty sure that she has never seen this object before. This is a baobab tree. It grows in Africa, close to where I was growing up, and you know, you don't see this thing in the USA, which is the entire life of my daughter. Okay, so something special is going on here, and it's not that anyone ever gave my daughter a definition of a tree. So somehow she is able to seamlessly and flawlessly recognize trees, okay, despite not having a definition. She has learned what a tree is. Now, how did that happen? How that happened is that, you know, through her experience, walking around with me in the yard, let's say, I say, well, that's a tree, that's a cat, that's a dog, that's a car, that's a bicycle, and so on and so forth. And this is all data that's being pushed into her mind, which she keeps. Okay. And now all of a sudden, you know, 5 years later or 3 years later, I come around and say, well, is that a tree? She says, yes. Well, is that a tree? She says, yes. Well, is that a tree? Yes. Well, is that a tree? No, that's a cat. Okay. Do you know the definition of a cat? Nope. Do you know the definition of a tree? Nope. But she gets it all right. So somehow, just by looking at pictures, some of which were told to her are trees and some of which were told to her are not trees, something else, she has managed to extract some working definition of a tree, some working pattern of what constitutes a tree, okay, even though she has never been told what a tree is. Okay, and that working pattern that she has extracted worked flawlessly for things that she never saw before. Okay. Now, in this whole story is embedded exactly what learning is. And, you know, our goal for this lecture is to pin that down. Okay? And then at the end of the day, we'll have a mathematical formulation, and that will be the formulation that pretty much we will use for the rest of the course. So, the punchline is, defining the tree is hard. That's kind of like writing down a formula for what is a tree. But it appears to be easy, both for the cat and for the 5-year-old girl, to recognize a tree after having been presented data on what are and what are not trees. So after having learned from data, it's easy for the 5-year-old to recognize trees. But it's hard for me, a very sophisticated 45-year-old, to come up with a definition of a tree. Okay. Let's look at another example.